Well, hi there, sports fans. Welcome to another exciting episode of Physics 12. And today we're looking at lesson 5.4. And today's lesson is going to be on something really heavy, gravity. I know, it's a pretty lame joke, but hey, you know, in physics, all of our jokes are pretty lame. So gravity, it was Sir Isaac Newton that did a lot of the groundbreaking work, sorry for the pun, on gravity. And he knew that at just about every point on the Earth, the force of gravity was about the same. And so it led him to conclude that, well, maybe it was the Earth itself that was producing this force of gravity. And then, as the story goes, with the apple that he saw fall from a tree, he surmised that if perhaps gravity was working at the treetops, maybe gravity worked at even greater distances, like perhaps from between the Earth and the Moon. And so he started to determine whether or not this was indeed the case. Was it the force of gravity from the Earth that was keeping the Moon in its orbit? And in turn, was it the force of gravity of the Sun on the Earth that was keeping the Earth moving in its orbit around the Sun? And he turned out to be right, actually. So he did a lot of the groundbreaking work on gravity. And so he was able to determine that, yes, indeed, it was the force of gravity of the Earth on the Moon that kept it in its orbit. And he also recognized that the force of gravity between two objects are equal and opposite. And so anytime that you have two masses, any two masses will produce a force of gravity between them. And the forces will be equal but opposite in direction. So here's what was initially determined about the force of gravity, is that the force of gravity varied inversely with the square of the distance. So this was an inverse square relation. And it was also noted that the force of gravity early on in experiments and things, that the force of gravity also varied with the product of the two masses. So the mass of the two objects also was a factor in determining the force of gravity, and it turned out to be the product of one mass times the other, and then divided by the distance between them squared. And from there, it was determined that the universal gravitation constant turned out to be 6.67 times 10 to the minus 7. So here is our formula for the force of gravity that was worked out by experimentation. So the force of gravity between any two objects that have mass, it's the universal gravitation constant, 6.67 times 10 to the minus 7, times the mass of the one object times the mass of the second object, divided by the distance between the two objects and squared. And the distance between the two objects was from the center. So again, we're working with the center of mass when we're dealing with the masses of the objects. And that becomes very important for large objects like the Earth and the Moon, etc. And the Sun, obviously, too, of course. So when you're dealing with large objects, then you have to use the center of mass, which is the center of the object itself. All right, so let's look at an example of this, how we determine the net force of gravity on an object. In this case, our object is the Moon. And we're going to determine the force of gravity on the Moon, the net force, from the gravitational force of the Earth and the gravitational force of the Sun. So we have these two forces here, and we're going to find the resultant force on the Moon when it's in this sort of a configuration right here. So at a certain time in the year, then the Earth, the Moon, and the Sun will be in this sort of configuration, and that probably happens a few times per year. And so we're going to find the net force on the Moon in that position. So I have the objects redrawn here. You can see I tried to color coordinate it. I've got a yellow sun, I have a white moon, I have a green Earth, of course, a green Earth. Or maybe the Earth should be a little bit more blue as well, have some blue in there. But in any case, so here's how they're oriented like so. And we have the force of the sun on the moon in this direction here. We have the force of the Earth on the moon in that direction like so. And we will say that they make a right angle in this case, just for our purposes of this example right here. We'll say that that is a right angle. So we need to get some numbers in here. We need the mass of the moon, which is 7.35 times 10 to the 22nd kilograms. We need the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. And we need the mass of the sun, which has been determined to be 1.99 times 10 to the 30th kilograms. So there's our masses of the objects. And the distance between them, the distance from the moon to the center of the Earth is 3.84 times 10 to the 8 meters. And the distance from the moon to the center of the sun is 1.50 times 10 to the 11 meters. So there's the numbers that we need to work with. And so here is our formula for the force of gravity right here. And now we can just go ahead and put in the numbers that we have here. So first look at the force of the Earth on the moon. And so putting the numbers in here, here's our universal gravitation force constant. The mass of the moon and the mass of the Earth divided by the distance between them squared. And again, your most common mistake is not to square this number here. So make sure when you're doing your calculations that you square the number that's in the denominator here. So if you punch your numbers in your calculator correctly, you will get 1.99 times 10 to the 20th newtons. So that is the force that the Earth is exerting on the moon. So that's one part of it. Now we need the other one. So the force of the sun on the moon. So again, our gravitational force constant, 6.67 times 10 to the minus 11. Mass of the moon, 7.35 times 10 to the 22nd. And the mass of the sun, 1.99 times 10 to the 30th. And the distance between the moon and the center of the sun is 1.50 times 10 to the 11. And again, make sure you square that number for your calculation. And if you do, then you should get 4.77 times 10 to the 20 newtons. All right, so there's our two forces. So we've got 1.99 times 10 to the 20th on the from the Earth on the moon, and we have 4.34 times 10 to the 20th newtons from the sun on the moon. So we have these two forces at a right angle, and then we can go ahead and find the net force. So the net force is going to be, we use the Pythagorean theorem here, and so the magnitude of the force ends up being 4.77 times 10 to the 20 newtons. And we can also find the angle between, or the angle that it makes, theta. Theta is tan to the minus 1, 1.99 times 10 to the 20 divided by 4.34 times 10 to the 20, and that gives you 24.6 degrees. And so our final answer then is the net force on the moon in this sort of configuration right here is 4.77 times 10 to the 20th newtons at 24.6 degrees east of south. And of course, south and east is kind of meaningless in this sort of a configuration right here. But just for the purposes of the way that we draw our diagrams, so that anybody looking at the diagram knows what you mean. Certainly when we're looking at things like planets and stars and our sun, of course, north, south, east, and west is not as meaningful, of course. It's just referring to the diagram that you make. So based upon your diagram, then we'll use our directions in such a manner.